conservation of momentum. It means the momentum remains constant. So conservation means constant. It is just like conservation of energy, where we say energy is constant. Here conservation of momentum means momentum remains constant. But how it is possible? Let us understand this. According to Newton's second law, we know that force equals to rate of change of momentum, delta P by delta T. This force is actually a net force or unbalanced force. Say I am using subscript n, which says the net force. Now supposing that net force acting on the body is 0, implies delta P by delta T equal to 0. Hence you can write delta P equal to 0, and delta P is nothing but change in momentum, which is final momentum minus initial momentum, equal to 0, and it implies final momentum equal to initial momentum. That means what is the final momentum you get? It is anyway equal to initial momentum. It means the momentum is not changing and momentum remains constant. So this is what conservation of momentum. So if you wanted to write a statement, you can write like this: when no net force is acted on a body, then its momentum remains constant. So this is the statement of conservation of momentum. Take an example like this. Say that a car moving with a constant velocity, and it is possible whenever the driving force F is equal and opposite to the frictional force small f. Therefore the net force Fn is equal to capital F minus small f, which is equal to 0. Implies we know that the velocity remains constant. So this is called uniform motion of the body. And let the car has mass m, and whenever this situation occurs, you can say that mass into velocity equal to constant, and this is nothing but momentum remains constant. Okay, let us take another way of understanding conservation of momentum. Think that there is a container, a gas container, and this container consists of gas molecules. As you know that all these gas molecules are not resisted, they move in random direction. Whenever they come towards another gas molecule, there is a collision occurs, and because of the collision, the gas molecule move in the different directions, and still they have their constant average velocity. Let us understand in detail. Say I am taking two gas molecules this way. One gas molecule of mass m1, and the second gas molecule, one gas molecule say mass m1, and the second gas molecule of mass m2. So this m1 gas molecule moving towards m2, and the m2 to move towards m1. Then what happens? The m1 mass applies a force on the m2. Say that force is F12. Similarly, m2 mass is also apply a force which is equal and opposite. And according to Newton's third law, we say that F1 equal to F21 minus of. It means action equals to minus reaction. This is what Newton's third law. For every action there is equal and opposite reaction. So it says that F12 is the action or the force acted by the mass m1 on m2. Then F21 is the force by m2 on m1, which is the reaction. So this Newton's third law is satisfied. At the same time, we can also prove that here the conservation of momentum is also satisfied. So how? Let us see further. F12 is the force acted on m2 mass by m1 mass. So m2 mass means, according to Newton's second law, mass into acceleration. So m2 mass into the acceleration is a. which is the acceleration of m2, and F21 is the force acted on m1 mass, therefore m1 into acceleration a. Okay, now coming back to the F12, so m2 into, so this is the acceleration of the m2 body, so therefore m2 has initial velocity u2, and because of the force application it has changed to v2. Similarly, m1 has initial velocity u1, and because of force application velocity changed to v1. So now what I do now, acceleration a is nothing but the final velocity minus initial velocity of the mass m2. So m2 final velocity is v2, initial velocity is u2 divided by time, say delta t. So this is acceleration. In similar grounds, the F21 is also m1 into the acceleration of the mass m1. So therefore, it is v1 minus u1 by delta t. So delta t should be the same because the equal time they are in contact and they separated. So according to Newton's third law, F12 equal to minus F21. So if you write m2 into v2 minus u2 by delta t equal to minus of m1 into v1 minus u1 by delta t. So if you see delta t get cancelled, and if we expand this, m2 v2 minus m2 u2 equals to minus of m1 v1 and minus plus, so plus m1 u1. Now just rearrange the formula. Take m1 v1 to the left hand side, so you can write m2 v2 plus m1 v1 equals to minus m2 u2. You can take to the right hand side, it becomes m2 u2 plus m1 u1. Then so what happened here, m2 v2 we can say that is the final momentum of the m2 mass. m1 v1 is the final momentum of m1 mass. Similarly, if you see the m2 u2, it is the initial momentum of the m2 mass, and m1 u1 is nothing but the initial momentum of the m1 mass. Since the force are acting on the two bodies, there might be the situation this way: m1 and m2 both are in contact this way, and this is what called collision. So here two situations you can imagine. One is before collision, one is after collision. So before collision, if you see, this is the diagram before collision. So here you see that this is before collision, because before collision the bodies are approaching to each other and then they collided. This is collision, they collided, and after that they separated this way. This is after collision. So before collision they have the velocities u1 and they have the velocities u2. So this is having the velocity u1, this is having the velocity u2 according to the previous diagram. And after collision, m1 has velocity becomes v1 and m2 has velocity becomes v2. Therefore we can say that according to this equation what you have obtained here, this one, what it says that total momentum before collision. So total momentum before collision means before collision you have momentum m1 u1 and m2 u2. Therefore m1 u1 plus m2 u2 is equal to total momentum after collision. So after collision, m1 m2 masses have the velocities v1 v2. Therefore m1 v1 plus m2 v2. Hence the conservation of momentum can also be expressed as total momentum before collision equal to total momentum after collision. This is how it proves that wherever the Newton's third law is applicable, there you have conservation of momentum also applicable, or else this conservation of momentum is another form of Newton's third law, because this momentum, conservation of momentum statement, total momentum before collision equal total momentum after collision, we have obtained because of this statement, action equal to minus reaction. Take one more example here. Take the rocket example. This is a rocket, and you know that rocket has rocket mass and some amount of gas inside the combustion chamber. So what happened, in the combustion chamber, the gas burns and gas comes as a gas jet, and gas jet in the downward direction this way. So this is the force F1 as the gas jet is coming the downward direction, which is called action, and due to that the rocket moves in the upward direction, which is reaction. See, the force is F2, reaction. According to Newton's third law, we can say that this F1 equals to minus F2. Now coming to conservation of momentum, how do we apply conservation of momentum here? Before the rocket launched, before launch, rocket plus the fuel, the total momentum is 0 because there is no velocity. Before launch there is rest state, so it is 0. So after launch also the momentum needs to be constant, and hence if the gas jet moves with the velocity v in the downward direction, obviously the rocket has to move with the same velocity v but in opposite direction. So that's why if I say the mass into velocity v, which is the momentum before the after the launch, which is the momentum of the fuel, or I can say gas jet, then minus mass into velocity of the rocket, which is again equal to 0 because m into v and minus m into v is 0. Therefore why it is 0? Because we, according to conservation of momentum, before collision how much momentum is there, after collision also it has the same amount of momentum. Means before launch the momentum is 0, so therefore after launch it also should be 0. And to make the momentum 0, if gas jet goes velocity in the downward direction, there should be some body in upward direction with negative velocity, and that body is nothing but rocket. That's why rocket always moves opposite to the gas jet direction. There are two types of collisions. One is called elastic collision, and the second one is called inelastic collision. So in elastic collision, two laws are applicable. Two laws. One law is conservation of momentum, plus conservation of kinetic energy. In inelastic collision, you have only conservation of momentum is applicable. So here conservation of kinetic energy does not applicable. Okay, now conservation of momentum means, say, take an example of mass, body of mass m1 moving with the velocity u1, body of mass m2 with the velocity u2, and they are collided this way, m1 m2. Okay, and after collision they are moving in the same direction. Say this is called one-dimensional collision, and the final velocities are v1, v2 for the masses m1, m2. So according to conservation of momentum, as we discussed earlier, conservation of momentum, you can write it as we discussed, total momentum before collision. So total momentum is m1 u1 plus m2 u2, which is before collision, equal to total momentum after collision, m1 v1 plus m2 v2. This is conservation of momentum law. Now conservation of kinetic energy. So this is also similar grounds, the same way as conservation of momentum, but you have to say total kinetic energy before collision. So total kinetic energy is half m1 u1 square plus half m2 u2 square. So this is total kinetic energy before collision equal to total kinetic energy after collision, which is half m1 v1 square plus half m2 v2 square. In real life, we can't find the elastic collision because always some energy is lost. So most of the collisions are inelastic only. When we talk about elastic collision, those are the ideal cases. Okay, take an example of inelastic collision. Say there is a body of mass. There is a body of mass m1 with the velocity u1, and there is another body of mass m2. Okay, and it is at rest state. Say its velocity is 0, and after the collision both bodies are attached to each other. m1 m2 are attached and move with the common velocity v. Now this is inelastic collision. So the first body moves the velocity u1, but the second body is at rest state, and when the first body hits the second body, both bodies are attached and move with the common velocity. It's a case of inelastic collision where energy is not conserved, kinetic energy is not conserved. Now we need to find out the common velocity v. This is need to find. Now how do we do that? Just apply the conservation of momentum. Whenever we have the case of collisions, always it is good idea to apply the conservation of momentum. So before collision, the total momentum means the first momentum of the body is m1 u1 plus second the momentum of the second body, which is m2 u2, but u2 is 0, it becomes 0 equal to, now after the collision both are stick together, and both are stick together, the total momentum means what we do, we take the total mass of the two bodies, which is m1 plus m2, which moves with a common velocity v, and hence the formula of v changes to m1 u1 by m1 plus m2. So that's how we can find the common velocity in inelastic collision.